Hi class. Today in chapter 15 we are going to focus on lipids. Lipids are the second classification of some biomolecules. The ones we've already dealt with are carbohydrates. Chapter 15 here is going to be broken up into two parts. In the first half we're going to look at what fatty acids are, waxes, and fats and oils. So what are lipids? Lipids are biomolecules that contain fatty acids or a steroid nucleus. So lipids are broken up into those two categories, either the ones that contain fatty acids or the ones that contain a steroid nucleus. These are solvents, but they're not
soluble in water. That brings us back to likes dissolve likes. Water is very polar and lipids aren't, so they don't dissolve. Lipids are named after the Greek word lipos, which means fat. Lipids are extracted from cells using organic solvents. Okay, so those were just some properties about lipids you needed to memorize. Here are the two ways to divide up our lipids. The types of lipids that contain fatty acids are waxes, fats, and oils, which are also called triacylglycerols, glycerophospholipids, and prostaglandins. In this class, we're only going to focus on the first. I'm going to leave the prostaglandins for biology or anatomy and physiology. The types of lipids that do not contain fatty acids classification, which we'll also look at in this class. So here is a flow chart just saying the exact same thing I just said, where lipids are broken up into two groups. So if you've noticed, we've got two lines coming off this first box. Our first grouping are those that contain a fatty acid, and the second group are the lipids that contain a steroid nucleus. So this molecule here with the rings is our steroid. Though the ones that have fatty acids are the prostaglandins, which we are not going to focus on in Chemistry 103, but we will look at these three in the green box. So you're going to need to be able to identify your waxes, triacylglycerols, and glycerophospholipids. Steroids then are going to be broken down into the cholesterol, bile salts, and steroid hormones. Okay, so starting off, what are fatty acids? Because they're the building blocks of a lot of our lipids we need to learn. So fatty acids are long-chain carboxylic acid. So basically they have that carboxyl group. And I'm hoping you can remember your carboxyl group. It has the carbon double bond oxygen bonded to the hydroxyl group, the OH. Okay, so basically a fatty acid is just a carboxylic acid, which you've already seen before, except it has a long carbon chain on it. They typically contain 12 to 18 carbon atoms. Because of that long hydrocarbon chain, they're insoluble in water. So even though they have that carboxylic acid group with the OH bond, which can hydrogen bond, that is offset by such a large amount of carbon and hydrogens, the nonpolar part. Fatty acids are saturated and unsaturated. So remember, saturated means it does not have any carbon-carbon double or triple bonds. Okay, it's all single bonds. But some of the fatty acids are unsaturated. So you'll see in a few slides that there's some that contain double bonds. Over here we have a picture of olive oil. Kind of deceiving that I have it on this slide with fatty acids. An oil is not a fatty acid. They're composed of fatty acids. And olive oil, for example, contains 84% unsaturated fatty acids and 16% fatty acids. So I don't expect you to know that point. It's just kind of a trivia point for you. Saturated and unsaturated fatty acids. So saturated have only the carbon-carbon single bonds. So notice we have this little zigzag here. This is a way that we show kind of a shorthand way of showing all of those CH2 groups. So every point here on this zigzag is a carbon with two hydrogens bonded. So it's a CH2. Then when you get to the end, we're going to end with our CH3 because carbon always has 4 bonds. But notice in the zigzag we don't have any carbon-carbon double bonds. So this would be a saturated fatty acid. In your unsaturated fatty acids, there's going to be at least one carbon-carbon double bond. So the one I'm showing you here has the double bond right here. But many of your fatty acids you're going to come to see here pretty soon have more than double bonds, more than one double bond. So some properties of saturated fatty acids, those that do not contain any double bonds. Saturated fatty acids contain only carbon-carbon single bonds. They're closely packed together. That's a really important point to memorize. So notice if I've got these nice straight zigzag lines, they're able to stack on top of each other pretty closely. Okay.
they have, because of that, because they can stack so closely together, they have a lot of areas to interact. So they have a lot of interactions going on between these long chains. Because of that, they have high melting points compared to your unsaturated fatty acids. Okay. Because they have high melting points, they tend to be solids at room temperature. Okay. So unsaturated fatty acids contain one or more cis double bond. Nature tends to put out your carbon-carbon double bonds in the cis formation instead of the trans formation. Because of this cis formation, the fatty acids have what we call kinks in the chain. So instead of being this straight zigzag line, it ends up, when you get to the double bond, it kinks the chain. So if you look at the picture here, your zigzag ends up having a kink, and then the rest of the chain ends up going off in a different direction because of the cis double bond. Remember your cis double bond, we have our hydrogens on the same side of the carbons and our bulky groups on the other side. Because of these kinks, the fatty acids do not stack closely together. Because of the kinks, they have very few interactions between the side chains. So notice this chain right down here isn't going to have a lot of interaction with this chain because it can't stack so closely together. Because they can't stack closely together, or because they have very few interactions with each other, they have a lower melting point than the saturated fatty acids. Because of that, because of their lower melting point, then they tend to be liquids at room temperature. So here are the melting points of some fatty acids. If we look at our first four here, they are saturated because I don't see any double carbon-carbon double bonds in them. So these ones are saturated. And the ones down here are unsaturated fatty acids. And if we just look at those two groups, sure enough, the ones that are saturated have a lower melting point than my top four saturated fatty acids. Another thing I kind of want you to know is the difference between the amount of carbons. So if we just look at my fatty acids that are saturated, so we're holding that variable constant, and what we change is the amount of carbons. Hopefully you remember this from organic chemistry, but the more carbons you add on, the higher the melting point is going to be. So the heavier the molecule is, the higher the melting point will be, and that's what we're seeing here. My first saturated fatty acid has 12 carbons, melts at 43 degrees, but if I go all the way up to 18 carbons, now it melts at 69 degrees Celsius. So melting point increases as the number of carbons increases, but your melting point decreases as you get more and more carbon-carbon double bonds. So here's a learning check. Assign the melting points of -5 degrees Celsius, 13 degrees Celsius, or 69 degrees Celsius to the correct fatty acid, and then explain why. So for starters, if you look at these three fatty acids, all of them have 18 carbons. So we're not changing that variable on you. What is different is the degree of saturation. In my first one, it's completely saturated. There's no carbon-carbon double bonds. So because of that, my zigzag lines are all straight. So those fatty acids can stack closely next to each other. So there's a lot of interaction. So that gives them a higher melting point. So we're going to assign the 69 degrees Celsius to the saturated fatty acid. Here, the difference between my next two is I've got one double bond versus two double bonds. So the more double bonds you get, the more kinks you have, and the less interaction you're going to have. So basically, the one with the two double bonds is going to have the lowest melting point at -5 degrees Celsius, and then the one double bond will have that intermediate melting point. Okay, so remember, fatty acids are the building blocks of the waxes, fats and oils, and fats and oils. So those are the three we're going to look at today. Waxes are esters of fatty acids and long chain alcohols. So just to refresh your memory, a fatty acid is a carboxylic acid, so it has this carboxyl group, and you're told that they are long chain fatty acids, so they have quite a few CH2s coming off of them. Remember, your alcohols they end with OH, so it's ROH, but that R group is going to be a long chain alcohol. So wax is formed between a carboxylic acid and a long chain, or a fatty acid and a long chain alcohol. So here are some examples of some waxes. So we have beeswax. So here's a few. And what I want you to see, I don't expect you to memorize these, but I do want you to be able to locate your ester group. Okay? And then if you see a lot of carbons on each side of this ester group, so you look to the left and there's a lot of carbons, you look to the right, there's a lot of carbons, and I want your brain to say, oh, this is a wax. Okay? It's an ester group. So what I plan to do on your next exam, on the final, because the final is not comprehensive, so it's just going to cover these last few chapters, is I'm going to give you a sheet with some different biomolecule structures, and I want you to be able to identify, you know, which one is the wax and which one is the triacylglycerol and things like that. Waxes are coatings that prevent loss of water by leaves of plants. And here is a review on the reaction esterification that we had in the last chapter. So esterification is the reaction of a carboxylic acid and an alcohol in the presence of an acid catalyst to produce the ester. So this is what we did in the last chapter. So here's the carboxylic acid, here is the alcohol, and if you remember, we broke between the carbon and the oxygen of the carboxylic acid, and we broke off the hydrogen on the second molecule. And so you circle the pieces that we're going to break off, and then you're going to switch places. So when you switch places between these circled groups, you end up with this ester. Now in this particular example, the ester is not a wax because it's only got one carbon on the left and two carbons on the right. But that's how we form the ester. And then the other product we have is water. So this reaction is going to be exactly the same for the formation of a wax. The only difference is the number of carbons we have. So here's a learning check. So we're going to break it here. And we're going to break between the hydrogen and the oxygen on the second molecule. And we are going to swap places. So I'm just going to start writing this compound from left to right. Sometimes you may have flipped over the molecule, but that's fine. CH2, I've got 14 CH2s. I still have this carbonyl group, but now instead of being bonded to the OH, it's going to bond to the other circle. So I have the oxygen and 29 CH2s, and then water is my other product. So this guy right here is a wax. Okay, so right here is a wax, and it's just an esterification reaction. Okay, so fats and oils, which are also called triacylglycerols. In biology, they call these triglycerides. Fats and oils are also called triacylglycerols. I talked about that. They are esters of glycerol. So I am going to want you to know what the structure of glycerol is. I'll show you in a second. It is produced by esterification, so the reaction I just showed you. They're formed when the hydroxyl group on glycerol reacts with the carboxylic acid group on your fatty acids. So I'll show you what I mean by that. So here is glycerol. So draw an arrow to this guy here and write that I want you to memorize that. This is glycerol, and notice it has 3 alcohol groups in it. So you're going to do esterification, but you're going to do it 3 times. So since I have 3 alcohol groups, I'm going to need 3 fatty acids to bond to this. Another thing to notice about glycerol is that these 3 carbons are covalently bonded. Okay? In biochemistry, since the molecules are so big like this, they tend to write them from top to bottom. In organic chemistry, we would have written glycerol like this. We would have just worked more from left to right and then put our OH branches up here. So this is glycerol, but you're going to see it written more like what I have here in the box. So notice, what I want you to notice is that these carbons along the backbone are covalently bonded together. Okay, so when these 3 hydroxyl groups react with 3 carboxylic acids, that's where we get the triacylglycerols. So you want to be able to look at this group right here and identify this as a triacylglycerol. Is it, well, I haven't told you that yet. Do my fatty acids, are they saturated or unsaturated? So hopefully you would answer that and say, okay, when I look at my zigzag lines here, my hydrocarbon ends, I don't see any double bonds. So this guy right here, my fatty acids are all unsaturated. They don't have to be, as you'll see in just a few more slides. So here's just kind of a schematic of a triacylglycerol, where you're going to have the glycerol backbone, they call it, so the 3 carbons here along the backbone. And then they're bonded to 3 fatty acids, and they're held together by an ester bond. So the formation of a triacylglycerol, start off, and we're going to keep just that general pattern, where you find your group that contains the carboxyl group, or the carbonyl group, and you're going to break to one side of that carbonyl group. And you're always going to break between, remember in organic chemistry we were breaking between an oxygen, a carbon and an oxygen, or a carbon and a nitrogen. Okay, so we're going to circle off the OHs, and then you circle off everything on the glycerol except the hydrogens. Notice what you have in the circle is going to stay stuck together because you've got these covalent bonds between the carbon. Okay, so you're just going to rewrite this molecule swapping what we have circled, and this is what you end up getting. You're going to end up getting 3 water molecules, and then our triacylglycerol over here. Here's a kind of another way of looking at it that might be easier for you. Instead of the circling and swapping what we have in the circles, if you set up your structures carefully, what you can also do instead is just know that you're going to be making 3 water molecules. So you're going to rope out 3 water molecules. So here you take off the hydrogen, because we said you always break between the hydrogen and the oxygen. So that's what you're always going to do on the glycerol molecule. And then you're going to take off the OH group on the carbonyl group, and that's going to make water. And then the oxygen here, which you've taken the hydrogen off, and this carbonyl carbon are going to bond together to make that ester bond. So the melting points of fats versus oils. A fat is a solid at room temperature, and it's prevalent in meats, whole milk, butter, and cheese, and things like that. Oils, on the other hand, are liquid at room temperature, so we kind of know this just from our life experience. They're prevalent in things such as plants, like the olive plant and safflower seeds. Oils have more unsaturated fatty acid building blocks. Now that should make sense, because I just got done saying that fatty acids that are unsaturated have a lower melting point than your saturated fatty acids. So if it's an oil, since it's a liquid at room temperature, I'm hoping it makes sense that that's going to have a lot of kinks in it, a lot of carbon-carbon double bonds. So some unsaturated fatty acids. So oils have cis double bonds. So I do want you to know that in nature, nature tends to produce your carbon-carbon double bonds in the cis formation instead of the trans formation. So oils have cis double bonds that cause kinks in the fatty acid side chains. These kinks do not allow the triacylglycerol molecules to pack closely together. Because of that, they're going to have lower melting points than your saturated fatty acids do. And because of that, then they're liquids at room temperatures. So here's kind of a picture of a triacylglycerol that has the double bond. So they're showing you the double bond right here causes the chain to kink, which causes it to have a lower melting point. So some percent saturated and unsaturated fatty acids in some fats and oils. If we go down here to our key, the yellow means polyunsaturated. Now, if you remember, the prefix poly means many. So many unsaturated is going to mean it's got many carbon-carbon double bonds. The orange line is our mono unsaturated, mono being a prefix for 1, so it's just going to have 1 carbon-carbon double bond. And the blue is the saturated fatty acids. So if you look at this guy here, if you look at coconut oil, it has got quite a bit of saturated fatty acids. And if we focus on the polyunsaturated, it looks like one of the better ones are going to be the safflower oil. Notice your melting point. Coconut has a melting point of 25 degrees Celsius, and safflower oil has a melting point of negative 18 degrees Celsius. So the higher the saturation, the higher the melting point is going to be. So some chemical properties of triacylglycerols. The chemical reactions of triacylglycerols are similar to those of alkenes and esters. So the one reaction you're going to need to remember from organic chemistry of alkenes is hydrogenation. where you're adding hydrogen to the carbon-carbon double bond. And then you're going to need to remember the reaction of esters, where you're going to form esters or hydrolyze esters. So those reactions are going to come up again. In hydrogenation, the double bonds in your unsaturated fatty acids are going to react with hydrogen in the presence of nickel or platinum. In hydrolysis, the ester bonds are going to be split by water in the presence of an acid, a base, or an enzyme. So we've talked about acid hydrolysis or base hydrolysis. Most of the reactions happening in our body are going to be catalyzed by what the enzyme catalysts. Okay, so to refresh your memory, hydrogenation. Hydrogenation of oils adds hydrogen to the carbon atoms in the double bond. It's going to convert the double bonds then to single bonds, and it's going to increase the melting point, because remember, the more single bonds you have and the less double bonds you have, then the higher the melting point is going to be. So hydrogenation then is the process of producing solids from your oils. So if you look at this picture, when you start off with oils that we get from vegetables, and when you hydrogenate it, that's how we make the margarine and some of our shortenings and things. So hydrogenation breaks the carbon-carbon double bonds and increases the melting point. Okay, so a quick review. Here is our carbon-carbon double bond. We're going to break one of those. When we break one of those double bonds, it's going to break the octet of these carbons, so we have to add something to it. And in hydrogenation, it's hydrogen we're going to add. So that's going to give us this molecule. These 3 lines means it's equivalent to this guy. So remember, you can write it this way. I would accept it this way. But if it's a multiple choice test question, they tend to write it with all the hydrogens written in the backbone. So here's an example, hydrogenation of this triacylglycerol. Notice that we need, for this particular example, and this is going to change, but for this one we needed 3 hydrogens. The reason we need 3 hydrogen molecules is because we have these 3 double bonds. So what happens is we break the double bond, we add hydrogen to each one of the carbons on each side of the double bonds, and when you go to write this new molecule, notice that you can condense it. You don't have to, but what scientists do is they don't want to write a whole bunch of CH2s. So when this carbon-carbon bond breaks, and we add hydrogens to each side, the CHs on each side of that carbon double bond turn into CH2s. So when you write this, if you're looking right to the right of my carbonyl group, I have 5 CH2s, and then this CH turns into a CH2, this CH turns into a CH2, and here I have 7 CH2s. So when you add up all those CH2s now, that's how we're getting the 14 CH2s. In a triacylglycerol, you don't need all 3 fatty acids to be the same, like in this particular example. So here's a learning check. Write the products of the following reaction here. Okay, I did not leave myself much room. I'm just going to try to grab a corner up here and write the products. So the first thing I do is I start off with my 3 carbons of my backbone from glycerol. And then I'm going to put on my 2 hydrogens, 1 hydrogen, 2 hydrogens. So let me add those on. My first carbon has 2 hydrogens. The middle one only has 1 hydrogen. Oops, this is a hydrogen. My bottom one's going to have 2. And then I'm going to add that oxygen. Because remember, I'm just drawing out glycerol, but I'm leaving the hydrogen that we had taken off. So the oxygen then, in forming my ester group, is going to be bonded to a carbonyl group. So this is always going to be the start of a triacylglycerol. It's going to look like this. It's what is on that fatty acid that makes it different. So when I look at this guy, it's got 5 CH2 groups over here and 7 on this side. But when I hydrogenated it, now notice I only have 2 hydrogen molecules in this example, and the reason is because I only have 2 carbon-carbon double bonds. So when I break this double bond and I make it a single bond, this CH is going to turn into a CH2, and this CH is going to turn into a CH2. And the same thing here. This is going to go to a single bond, so these are going to be CH2s. So in a row, I have a total, if I add up this 5, 7, and the 2 new CH2s, up here I'm going to have a total of 14 CH2s. And ending up with my CH3 here that's on the end. This one here in the middle, it didn't have any double bonds, so I didn't have to hydrogenate it, so I'm just going to copy that exactly like it is. So 14 CH2s ending with a CH3. This molecule here, I'm going to have 5 plus 2 more plus the 7 is going to bring me down to 14 again. In this particular example, we end up with 14 CH2s, but that won't always be the case. So there is the formation of my triacylglycerol after I hydrogenated it. Okay, so you need to memorize that when you see hydrogen being added, and you don't have to memorize the catalyst, I'm always going to give that to you. So just memorize that when you see hydrogen as one of the other reactants, it's going to attack the carbon-carbon double bond. It's not going to do anything to my ester group. Okay, so here is the solution. What effect would hydrogenation have on the shelf life of the food product? So if you remember that alkenes are much more reactive than alkanes. The only reaction you had to memorize for alkanes was that they were the combustion, complete combustion, because alkanes are fairly stable, but alkenes has several more reactions. We only took you through a couple, hydrogenation and hydration, but it goes through many more reactions because that carbon-carbon double bond is more reactive. So when you hydrogenate an oil, that's going to increase the shelf life because the molecule is going to be more stable once it's been hydrogenated. All right, cis and trans fatty acids. So unsaturated fatty acids can be either cis, and remember, here's cis where you have the bulky groups, your alkyl groups on one side of this carbon-carbon double bond, in which case then you're going to tend to have the hydrogens on the other in this class, keeping the molecule simple. So this is going to be cis, so just to refresh your memory. Trans is going to have the bulky groups on the other side. Hydration and trans fatty acids. So most naturally occurring fatty acids are going to be with the cis bonds. During hydrogenation, some of the cis bonds are converted to trans double bonds. So if you're doing complete hydrogenation, which is what I expect you to do if I ask you to do hydrogenation, where every single carbon-carbon double bond is hydrogenated, that's going to give you just a saturated fatty acids. But sometimes when you are trying to control the melting point of things, you don't do complete hydrogenation and you do partial hydrogenation where you still leave some double bonds in. What tends to happen when that chemistry is happening, the reaction, is the cis double bonds end up converting into trans double bonds when you're doing a partial hydrogenation. In the body, trans fatty acids behave like saturated fatty acids. So I don't know if you caught this. We had a slide where, the first slide where I showed you fatty acids and some that were unsaturated. So if I drew out a fatty acid here, this one right here that I have is saturated. There's no double bonds in it. If I put a trans double bond in here, it ends up still being fairly zigzagged. A trans bond does not cause the big kink bonds that your cis do. So cis bonds cause the chain to be kinked, where your trans bonds keep it somewhat linear. So that the last bullet, oops, let me go back. In the body, trans fatty acids behave like saturated fatty acids because they can still pack on each other pretty closely. It's estimated that 2 to 4% of our total calories is in the form of trans fatty acids. And several studies report that trans fatty acids raise the LDL cholesterol and lower the HDL cholesterol. So this is kind of considered, the HDL cholesterol is what's considered the good cholesterol that you want to have. This guy right here is the good one. So you want to have high levels of your HDL, and you want to have low levels of the LDL. One way I heard an instructor say to memorize that is the L here stands for lethal, and I can't remember what they said now. I think the H is for happy or something like that. But there's some studies out there that say trans fatty acids will raise the bad cholesterol and lower the good cholesterol. The only bullets that I would expect you to memorize from this slide are these first two. I wouldn't test you on the other two. So true or false question. There are more unsaturated triacylglycerols in vegetable oil than in margarine and shortening. And hopefully you said yes, because margarine and shortening have a higher melting point than vegetable oil. So vegetable oil is an oil because it has a higher amount of unsaturated triacylglycerols. B, vegetable oils have a higher melting point. That's going to be false. Vegetable oils have a lower melting point than fats. So we said this one up here is true. Hydrogenation of oils will convert some of the cis bonds into trans bonds. That's true, assuming that you don't completely hydrogenate where everything would go to single bonds in that case. Animal fats have more saturated triacylglycerols. True. So if it's a fat, it's going to be mainly saturated. If it's an oil, it's going to have some unsaturation. All right, so that was hydrogenation. Switching over to hydrolysis. In hydrolysis, the triacylglycerol is going to split into glycerol and your 3 fatty acids. So it's going to be the reverse of esterification where we made the esters. Now we're going to break apart the esters. An acid or an enzyme catalyst is going to be required for this reaction. So there's our acid symbol. So here is my triacylglycerol. Is it a saturated one, or let me ask that different. Is this a fat or an oil? Just as kind of a side question. Hopefully you said this guy is going to be a fat. We know it's a fat because when we look at the carbon chain off my fatty acids, they're all saturated. Okay, so I want you to be able to do that. So starting off here with this triacylglycerol, I see water, which means I'm going to hydrogenate it. Really, I have a typo here because I'm going to need 3 waters, right? Because I have 3 ester groups I need to break. Now, where is this ester going to break apart? Am I going to break it on the right side of my carbonyl group, or am I going to break it on the left side? And hopefully you said the left side, because we always break between the carbon and the oxygen. So this is the group we're going to break off. And then the first thing I would do with my water molecules is I would write them as HOH. So I've got 3 water molecules. I'm just going to write over this guy. And remember, we break then between the O and the H. It doesn't matter which one you break. And then I'm going to switch places between my 2 circles. So on my oxygen, I'm going to have these 3 hydrogens, so that's going to give me my glycerol back. And then my 3 fatty acids, in this particular example, I have the same 3 fatty acids, but you don't always end up with the same 3. But since these are the same, I should end up with 3 fatty acids after I hydrolyze. So once again, notice, when you break apart your ester of your triacylglycerols, you're going to be left with 1 glycerol and 3 fatty acids. In this particular case, those 3 fatty acids are the same. So hydrolysis of a triglyceride, which is another name for triacylglycerol, follows the same pattern as hydrolysis of your esters that we studied earlier. So here's just what we did back in organic chemistry, where we broke between the carbon on my carbonyl group and the oxygen, and I broke between the hydrogen and the oxygen on my other molecule. And then I swapped places between those 2 circles, which is going to give me my carboxylic acid back, which we call a fatty acid in biochemistry. And I'm going to get my alcohol back, which in this case in biochemistry is going to be our glycerol. So it's actually going to be 3 alcohols bonded together. So here's a learning check. Write the products of the following reaction. So first thing I notice is that it's water. And I would probably write this as HOH if it were me. And I'm going to remember I have 3 of them. So if you want, you can write HOH 3 times. I find my carbonyl group, and I remember that it's going to split between the carbon and the oxygen. So I'm going to break off this point. Now remember, this is my glycerol. So I really don't even have to really think about this very hard. I could just say right off the bat, one of my products is going to be glycerol back. So that's the part I broke off. I've just rewritten it. It's going to get the hydrogen that I break off from my other molecule. So I'm going to circle the OH just to keep the circling the same. But these 3 hydrogens are what's going to go back onto my glycerol. So there's the glycerol. And then the other product I'm going to get are these 3 fatty acids. Now notice in this particular example, let me look closely here, it looks like the first fatty acid and my second fatty acid are the same. They've got 5 CH2s and then a carbon-carbon double bond and 7 CH2s and CH3. So do you see that this top one and this bottom one are the same? So when this breaks off, I'm going to end up with 2 of them. So So let's just go ahead and do that. What am I going to put on this carbon that I break in his octet? Remember, I'm swapping places between my two circles. So this OH group here is what's going to go on this carbonyl carbon. So I am just going to flip over my OH so that that oxygen is next to my carbonyl group. And then I have 5 CH2s. Nothing broke apart this carbon double bond carbon because I needed hydrogen to do that. And then I have 7 CH2s ending with my CH3. So there's 2 of them. Now I have to write this middle fatty acid. So I have my HO that I had from the water bonded to that carbonyl group. And then in this particular one, I've got 14 carbons ending with a CH3. So those are the 3 molecules I end up with. Just as a quick side note, is this very first structure that we were breaking apart, is it a fat or an oil? And hopefully you say that this one right here is an oil because of these carbon-carbon double bonds in the triacylglycerol. Another reaction, saponification in soap. We've talked about this in organic chemistry, so it's just coming up again. Saponification is the reaction of a fat with a strong base. It splits the triacylglycerols back into glycerol and the salt of a fatty acid. So when you're hydrolyzing with base, you don't just end up with your 3 fatty acids. You end up with salts of the fatty acids, which, remember, salts are ionic compounds. Salts have a cation bonded to an anion. Ran off my board. Saponification is the process of forming soaps. You can, 2 of the common bases that we do saponification with is sodium hydroxide and potassium hydroxide. If you use potassium hydroxide, that ends up giving you a softer soap than sodium hydroxide. So here is an example. So this is just a review of base hydrolysis from organic chemistry. So I just grabbed this slide from back when I was teaching you saponification back with esters, the first time we talked about esters. So base hydrolysis or saponification is the reaction of an ester with a strong base. It's going to produce salts of a carboxylic acid. And I want you to memorize that a salt of a carboxylic acid is also called a soap molecule. And then you're going to get your alcohol back, because remember, we're just breaking apart that ester group. All right, so in terms of a triacylglycerol, so looking at this one right here, tell me real quickly, is this a fat or an oil? And I hope you say that it is a fat, because I don't see any carbon-carbon double bonds. So if I wanted you to take saponification of this triacylglycerol, you are going to add 3 sodium hydroxides or any strong base. You need 3 of them because we have 3 ester groups that we're going to break. So this is hydrolysis. This is a base catalyzed hydrolysis. So we're still doing hydrolysis where we break apart with water. We're just not showing the water. We're trying to keep it simple. So we're trying to keep that same schematic where you break between the carbon and the oxygen. And on your second molecule, what is it you break off? So I'm going to circle this while you think about that. So you always break between the carbon and the oxygen on the molecule that contains that carbonyl group. And where you break on your second molecule is between the oxygen and the hydrogen. And then you're going to switch places of the circles. So what is it that I am going to end up having on my circles? Well, if I put this NaO over here, I have to put this glycerol backbone where this circle is. So that's going to give me glycerol back, just like we always get. So here's my glycerol molecule. You're always going to get glycerol when you hydrolyze a triacylglycerol. But in this particular case, I'm going to have 3. So what is it that I put on this carbon? You're going to put the NaO, and you have to think about, do I have to flip it over? And in this case, we don't want to flip over the NaO. We want to keep the oxygen next to these 3 carbons. Okay. In this particular case, my fatty acids are exactly the same. They're saturated with 16 carbons. So notice, however, that when I write this, oh no, here's just the one step. You can put this positive and negative sign in here, or you could have just put on your NaO without showing that plus or minus sign. And that is our soap molecule. Notice it is the salt of a long chain carboxylic acid, or the salt of a fatty acid. So how is it that soap's clean? A soap contains the non-polar end. So here is my little zigzag showing all my CH2s ending with a CH3. All soaps are going to have this, a big long non-polar tail. Let's see, and then that non-polar tail is going to dissolve in the non-polar fats and oils, because remember, fats and oils are non-polar, and the hydrocarbon end of my soap molecule is non-polar. So the zigzag area is going to want to be around fats and oils, because likes dissolve likes. And then the polar ends, so over here on my soap molecule I have this polar side, that's the salt area, the cation and the anion, very polar. That's going to want to be around water. So what happens is the nonpolar part embeds itself into the grease, and the polar heads don't want to be around the grease, so they end up staying on the outside, and you get what we call a micelle, which is the spherical blob, a micelle, which is able to then dissolve in the water. So usually fats and oils and water don't mix, they make the two different layers, but if you add a soap you can actually get the oil to dissolve into the water because it forms these spherical micelles. And here's just a little piece of trivia as kind of a side note. I won't test you on this, but it's pretty interesting, I think. Alestra came out in the market, I think, like the early 1990s. And it was dubbed a fat substitute because it felt and tasted like a fat, but our bodies didn't recognize it as a fat. So Alestra was used in foods as an artificial fat. What they had is they used sucrose. So here is the sucrose molecule. Remember, sucrose is one of our carbohydrates. And so here's the two rings of sucrose. Remember, it's a disaccharide. And sucrose has all those hydroxyl groups, all those OH groups. So when they made Alestra, they took all those hydroxyl groups. So instead of using a glycerol, they used sucrose as the backbone. And they put carboxylic acid, they reacted with the fatty acids on all the OH groups on the sugar. And they got something that had the same texture as a fat. So Alestra is sucrose linked by ester bonds to several long-chain fatty acids. It's not broken down in the intestinal tract. So some companies actually pulled it from the market when it was found to cause things like diarrhea, and there's studies showing that it kind of inhibited the absorption of some calcium ions and things like that. However, it still is out there in the market. So some of your potato chips and things still do contain Alestra. So it's something to keep in mind if you're interested in that.